Welcome back. In the second part of this lecture, we're going to look at some more techniques for solving logarithmic and exponential equations. So we looked at the case where you have an exponential function on one side and just a constant on the other, and we've already looked at how we can solve those. But what if we get it to the point where there's two exponential functions and they don't have the same base? If they had the same base, then it would be an easy problem for us to solve because we could just go right ahead and say that the powers should be equal to each other. However, when we have different bases, then it's not necessarily true that the powers are equal to each other. So unfortunately, we don't have a quick and easy solution in that way. But we can still use our power of logarithms to help us solve our equation in the same way that we did previously. If you were to take natural log, or any log of both sides of the equation, then those powers could be brought down in front, and then you could use algebra to solve for your variable x after that. I'm going to do this problem in a couple of ways. Or at least I'm going to start off doing it a couple of ways, and then I'm going to actually do my solution involving logarithms. So it is possible, for example, for you to use other kinds of logs other than natural log here. You might decide, for example, to start off taking log base 3 of both sides of the equation. And that does some nice things on the left side. Since 3 and log base 3 are inverses of each other, then log base 3 of 3 to some power should just leave you with whatever that power is. And then on the right side, the power would come down in front. And then all we would have to do is expand the right side, isolate the x, and solve for x. So this was taking log base 3 of both sides. You could also take log base 2 of both sides. And then the opposite would happen. It would be the right side. Log base 2 and 2 would undo each other. And on the left side, the power would come down in front. And then again, same sort of thing. We could expand the left side, then isolate x, and then solve for x. But I'm going to solve this, instead of using log base 3 or log base 2, I'm going to use natural log. So I'll take natural log of the left side of the equation and natural log of the right side. And the reason I'm using natural log is, again, if we were interested in finding the approximate value afterwards, it would be nice to have things already written, either in terms of natural log or log base 10. So that's why using natural log here seems to make sense. Just going to expand what we have on the left side. So 3x natural log of 3 plus 1 times natural log of 3. On the right side, we'd have 4x times natural log of 2, and then minus 1 times natural log of 2. And to finish the solving, I'll bring everybody with x's to one side. So 3x natural log of 3 minus 4x natural log of 2. And I'll bring the natural log of 3 to the other side. There we go. And then I can just factor out the x on the left side. And then dividing by that expression will give me x. So that x is equal to negative natural log of 2 minus natural log of 3 all over 3 natural log of 3 minus 4 natural log of 2. Or if you don't like all those negatives, you could multiply top and bottom by negative 1 to give you natural log of 2 plus natural log of 3 all over 4 natural log of 2 minus 3 natural log of 3. And that's how I'll phrase my answer here. So I'll say in my solution set, that would be the one value that I have. Natural log of 2 plus natural log of 3 over 4 natural log of 2 minus 3 natural log of 3. I will say, though, while we're here, that that answer could be written in a bunch of different ways. I'm not expecting anybody to do this, but you could, for example, combine the two terms in the numerator and say natural log of 2 plus natural log of 3 is natural log of 2 times 3. So the numerator could be rewritten as natural log of 6. Same thing with the numbers in front here. These could be brought in as powers. That could be really on the bottom to natural log of 2 to the 4, which is the same thing as 16, minus natural log of 3 to the power of 3, which is 27. And then if you wanted to, this last part that we have, natural log of 16 minus natural log of 27, that would be natural log of 16 over 27. So just to be aware of this, that even though we have an answer here in terms of logs that are natural logs, even that answer could be expressed in a completely different looking way. So the answer that I have is equivalent to natural log of 6 over natural log of 16 over 27. It's just, I'm not expecting anybody to go that extra step, and it's totally fine, and I think it's a good way to save time. Just leave your answer in that form. Now, one other thing for us to keep in mind is that our old techniques that we had, common factoring, doing a substitution, those sorts of things can come back again here, even when we're talking about exponential functions and logarithms. So, for example, this equation, it's a logarithmic equation, so we will have to check our solutions later on. But this is one that I could solve by factoring. So you could factor out of the first two terms a natural log of x, leaving a natural log of x minus 1. You could also see the same thing via a substitution. If you were to let u be natural log of x, then that means u squared would be natural log of x whole thing squared. And you would have the equation u squared minus u, which maybe makes that common factor a little bit more obvious. Either way, we come up with two potential solutions. Either natural log of x is 0, or natural log of x minus 1 is 0. And that gives us two solutions. If natural log of x is 0, then that could be rewritten as the exponential equation e to the 0 equals x, or x equals 1. If natural log of x minus 1 is 0, or if natural log of x is equal to 1, then that means e to the 1 equals x. Again, rewriting it as an exponential equation. Natural log is log base e, so I rewrote it as e to the power of and switched the inputs and outputs. So I have two potential solutions. I have 1 and e to the 1, and if I were to check my solutions, on the left side, you would have natural log of 1 squared minus natural log of 1. And we know natural log of 1 is 0. And so you'd have 0 squared minus 0, which is equal to 0, which is, of course, the right side. If you check x is equal to e to the 1, then on the left side, you would have natural log of e to the 1 squared minus natural log of e to the 1. And we know natural log and e are inverses of each other, so natural log of e to the 1 is just 1. So we would have 1 squared minus 1, which is 0. And of course, that's also equal to the right side. So both of these turn out to be solutions. Both 1 and e to the 1 happen to be solutions of our original equation. One thing I do want to be careful about here, just in case anyone is perplexed, be careful reading this, that when we say natural log of x in brackets squared, that's a natural log of x times another natural log of x. It's not the same thing as just squaring the x. So if you're wondering why did I not take the power and put it in front, the reason that was the case is because the power is not on the x. The power is on the entire natural log. So I didn't have the option of bringing the power in front. It would have been a different story if I had had natural log of x squared minus natural log of x. Then, in that case, without brackets, the power would just be on the x, in which case it would be fine to bring your natural log of x, or bring the power of 2 out front. But that's not what we had, so that's not what I did. All right, one last one to look at here, and this one may not be as obvious. With the first one, we had pretty clear common factor of natural log that could come out. And even if you didn't see that, a substitution might have been pretty obvious. For this, we have 4 to a power, and we've got 2 to a power. So we have different bases. But one thing you might notice, of course, is that 4 to the power of x could be rewritten in a base of 2, since 4 is the same thing as 2 squared. And so 2 squared to the power of x is 2 to the power of 2x. So really what we have here is 2 to the power of 2x, but that's the same thing as 2x that's been squared. So that's kind of my thing that I have here. I originally have 4 to the power of x, but that's really 2 to the power of x that's been squared. And now we can see that this is something where we could do a substitution. We could say, let's let u be 2 to the power of x. So that means u squared would be 2 to the power of x squared, which is the same thing as 2 to the power of 2x, which is the same thing as 4 to the power of x. So we wind up with u squared minus u plus 8 equals 0, or minus 6u rather, plus 8. And this factors very nicely. And we have two solutions for u. U is 4 and u is 2. But then, of course, don't forget that we need to go back. U is 2 to the power of x. So really 2 to the power of x is 4. 2 to what power gives us 4? The power is 2. 2 to the x equals 2. 2 to what power gives us 2? The power is 1. And now I've got my two solutions, 1 and 2. This was an exponential equation, so I don't need to check my solutions, although I certainly can. And if you check your solutions, you will find that left side and right side are equal for both of those values.